is that I now know that I know so little.
The only thing I think, the only people that know more than teenagers is adults on the internet.
Oh, yes, they know a lot. That's true. Which is good coming from me because I'm very opinionated. So I really shouldn't criticize other people. But I do because I can. Okay, let's get this show on the road, everyone. Good morning. We're basically working on vectors and we're going to see how far we can get. I believe the last thing I talked about was unit vectors, so let's start there. Suppose I have a vector in its ijk notation. And I do that. Then what I'm asking you essentially to do is to find the length of that vector. So that would be 4 odd 9 odd 16, which is what the square root of 29. So if I call that vector u, then a unit vector is a vector parallel to that. Imagine that was my vector, but its length is 1. And the formula for getting that is 1 over the length of the vector times the vector. So in this case, it's 1 over the square root of 29. And the vector is this guy. I don't like this notation, me personally, but you know, I want to show you it being used. Now, if this could be simplified, you know, if it was like 2 root 3 or something, you would do it. But I'm pretty sure 29 is going nowhere. And this is the unit vector, which is parallel to u, but whose length is 1. Let's just go. Suppose we have the same vector u. I'm going to write it in component form now, just to make my life easy. And I ask you to find this vector. Find a vector w that is parallel to u, but whose length is 6. So here's the puzzle. I got my vector u, and I want another vector 6 times as long. Right? That's all I want. Any ideas how I would go about finding such a vector? We've kind of done half of it here.
Well, you could find the length of your current vector, and then you could multiply it by 6.
Oh, so you could take this answer and multiply it by 6, couldn't you? So if you want to get that vector, let's call it w, wouldn't it be 6 times?
Wait, but isn't that just 6 times the length of u, not the length is 6?
Oh, I'm doing 6 times the length of the unit vector. So that will be 6, won't it? Right? And I'm using this guy, right? That's the unit vector. And in that case, it's 6 times this fella. So what would that get me? 12 of these guys, 18 of these guys, and 24 of those guys. So if you want to find a unit vector, you just find the length of the vector and divide all the terms by it, and this is what you get. If you want to find a vector that's parallel to the original, but is of a length 6 or 10, then just take 6 times the unit vector. In other words, I mean, there are other ways to do it, but I'm thinking, wouldn't it be easier just to get the unit vector first and then multiply everybody by 6? You know, just, who knows, maybe the next time it's 3/7 or something really messy, right? Wouldn't it just be easier to get a unit vector and then just multiply everybody by 3/7? I'm making an assumption here, which I probably shouldn't, that WebAssign is going to be happy with this technically speaking, shouldn't I rationalize all these denominators and make them look pretty? But, you know, for time purposes, I'm cutting corners. So, well, if I give you a vector, are you comfortable you know how to find a unit vector? If I give you a vector, are you comfortable you could find one that's parallel to you, but whose length is 6 or 10 or 49 or whatever fraction you like? We got right. Okay, so that is, what kind of questions is that for? Well, that would be questions 11, asks you things like that. So does question 12. So does question 13. Okay, now we're moving on to, I believe this is the name. At least it's going to be the name I'm going to call it. We're going to look at things called force diagrams. And a force diagram is one of those guys where, have you ever seen them where you have two forces and they pull together and you want to get the resultant force? Do you have a different name? Maybe I should use the different name. What do you call these stories? Force diagram work, you know, just so we using the language, right? Now, to be able to do this, we are going to have to find what is called the horizontal and the vertical component of the force. Basically, it's a vector. And these questions are going to be in 2 dimensions. We're not even going to go there in 3 dimensions because that's somebody else's problem, not ours. It's not a calc problem. Right. So suppose I have a vector u and it's 5, 1, and I have another vector v and it's 3, 2, right? And we imagine these 2 vectors. Oh, let's do a story with a boat. They like boats. So here's a boat, and the vector u is pulling like that, and the vector v is kind of pulling, and as I say, these are not drawn to scale, is pulling like that. Wouldn't we like to know the resultant vector? What you get when you add them? And maybe you'd like to know the horizontal force, because won't the horizontal force be kind of the force that you're using to pull it that way? And the vertical force, in this case, I guess it's not vertical, but it's going that way anyway, is what the vertical component is. So first thing you do is you combine the forces together. Now, isn't that simple? Just add and add. Agreed? And there is a formula for calculating horizontal and vertical components. So if I draw a little picture of what that might look like. Wouldn't the vector u plus v look like this? Wouldn't it be 8 along and 3 up, right? If you want to imagine a little triangle for it. If you want to get the x component, it is the magnitude of the vector times, oh, by the way, that guy's got an angle, hasn't he? We'll call it theta. So the x component is the magnitude of the vectors times what? Cosine or sine?
Cosine, I think.
It is, in fact, cosine, you're right. And do you want the y component? It's the magnitude of the vector times the sine. Now, in this question here, if you wanted to know it, I guess we'd need to find theta, wouldn't we? And we're going to have to do decimals here because don't expect exact values because these are engineering questions and nobody gets perfect numbers when you do real life. So what would I use to find the size of angle theta in my picture?
If it was me and I was looking at this problem, I would say that 8 squared plus 3 squared equals the square root of 8 squared plus 3 squared. And that's going to give me the hypotenuse. And then I would use this sine of
Or you could just do the inverse tan of 3/8, can't you?
yeah, but then you won't know the magnitude of the combined vector.
Well, you will eventually if you need it. And you're quite right. We just do Pythagoras, so I might as well do that. 9 and 64. There we go. Okay. Now, can do inverse tan to get the angle. Make sure your calculator is in degrees because we're engineers and engineers don't know what radians are. So inverse tan of 3/8. And the answer I get is about 20.6 degrees. So you want the x component. It's going to be square root of 73 times the cosine of 20.6 degrees. And if you want to know the y component, it's square root of 73 times the sine of 20.6 degrees. And that's just button pressing. So the square root of 73 multiplied by the cosine of 20.6 is, oh, I'm just going to call that 8 because it's darn close to it. And the next one is the square root. Why do I need to do that? I already have the x and y components, but there's a verification. Won't those guys end up being 8 and 3? Right. So let's put a story together in the way that these questions typically get done. So we're going to have an aircraft that's flying east, and it's flying east at 500 miles per hour. And I'm going to call that vector u, because I have no imagination. And we have some wind that's behind the aircraft, and the wind is blowing this way. And the wind is blowing with an angle of 30 degrees, and the wind is 50 miles per hour. Now, you know how these stories go, is it, aren't we going to find out what's the speed of the aircraft and what is the angle that it's actually going to be traveling at, right? Now, in this question here, aren't we, we'll call this vector v, right? Aren't we going to add these two vectors together? But to be able to do that, the way this information is given, aren't I going to have to find the x and y components? So let's do the aircraft first. And the aircraft I'm calling u, and would you agree that it's 500, 0? Isn't that a horizontal 500? The speed is essentially the length that we're going to use to represent that vector. Now, if we do the wind, well, I'm calling that guy v, and eventually I'm going to have the answer to it, and it's going to go in here. But how am I going to get the wind? Well, I need to find its x component, which goes in here, and then its y component, which goes in here. And its x component is the magnitude of the vector times the cosine of its angle, and its y component is the magnitude of the vehicle, the wind, I should say, times that. And so the magnitude is 50 because that's the guy, and the angle is 30 degrees. And the magnitude is 50, and the angle is 30 degrees. And here we go. 50 times cosine of 30 is about 43.3. Put this in red so it sticks out. 43.3. And we do the one underneath it. The y component is 50 times the sine of 30 degrees. And the answer I get is a nice 25. So what you do in these stories is you find the vectors for each of these, right, the aircraft and for the wind. And so I'll call it W. And W is what you get when you combine those two forces together. When you combine these two forces together, it's going to be 500, 0, this one, plus the wind, just this one. And that adds up to being 543.3, 25. Now that vector would probably be this fella. Would you agree that the aircraft gets blown off course somewhere between the horizontal and the 30 degrees? That seem reasonable? Right. This is the components. This tells you 543 along and so many up. But we don't want to know that. We want to know the speed of the aircraft, right? The green one. We want to know its length. And we want to know its angle. And I think the angle we'd probably like to know is that angle in there. Would you agree? Yeah. Well, we just kind of work on this. The magnitude of this vector is 543.3 squared plus 25 squared, which is kind of what Tim was doing, because he's used to these. And so that's square root of 543.3 squared plus 25 squared. And the answer I get is that, which is, and don't you call that, because I've been in lots of aircraft, isn't that called a tailwind? And the result is, doesn't the aircraft actually get a little boost to its speed? And I can tell you this because I've flown a lot, not lately, but I hope to return there soon, back home to Scotland, that when you fly west to east, in other words, fly to Scotland, it takes less time than coming back. And it's not because the aircraft, you know, speeds up. In one direction, the Gulf Stream, I think it's called, the Gulf Stream is pushing you. And in the other way, unfortunately, isn't it stopping you, right? Not totally, but slowing you down. And I think the difference is about somewhere between 45 minutes and an hour, depending on how strong the wind is. So that's half of it. Oh,
I have a question.
Yes.
So instead of doing like the magnitude of V times like the cosine of theta, could you just like make a side triangle and do the work there instead of just plugging it into the formula?
Oh yeah, you could do a right angle triangle and do it that way. Is that the way you were taught?
Yeah, that's the way that makes more
Just
sense in
keep
my
doing
head.
it. Just keep doing it. I'm doing it more of a formula way, but you know, that makes perfect sense. Oh, now we still need to get the angle, don't we? And the angle is the inverse tan of the y component divided by the x component. In this case, then, it's going to be the inverse tan of 25, the y component, divided by 543.3, the x component. So inverse tan of 25 divided by 543.3, close the damn thing. And I am looking at, wow, it's about 2.6 degrees. Agreed? Which isn't much. But if you fly 1,000 miles, couldn't that make a big difference if you didn't pay attention when you arrived? Now, today's navigation, that is not a problem. In fact, I believe what aircraft do is, if they want to fly due east. Don't they actually fly 2.6 degrees off that? Now, what will that 2.6 do? Well, the wind will straighten you up and you end up flying east. So if they know what direction they're being knocked off course, can't you compensate for that in your flight? So that you're basically going to fly straight to Glasgow, or wherever it is you want to go to, and not just keep going off course and then, okay, time to turn, to get back where we need to be.
This is why a bunch of carrier-based airplanes were lost early on in like the 1930s and 1940s, because they would literally take their speed and their direction of heading and add up all the vectors on a little map they had in their cockpit, and then figure out a vector back to the carrier after factoring in the carrier's speed. And you're trying to find.
So you try to say that somebody died because they didn't do this right?
Yeah, there's actually quite a famous flight where they got lost over Bermuda, and it's theorized this is what they did wrong.
So the next time somebody says to you, well, you'll never die, calculus can't kill you, you can say, oh yes it can. But most of you are probably not going to do this by hand anymore. Although I've been told by people in the Navy, and it's probably true even today, that don't you still do dead reckoning just in case the machinery gets scuppered? So you still know how to do it the old-fashioned way with traveling in this.
I was talking to my friend who was on submarines for most of his career, and I worked with him, and we were talking about the Connecticut that ran into something in the ocean, and he was like, yeah, you're supposed to keep track of your location and have a guess, and then the computer does it, and you compare the two, and then every once in a while you make sure you're actually correct, like go up and look at the stars or something. He didn't tell me how to do that, but so yeah, people do this on a submarine all day. So
this is relatively whatever the word I'm looking for, relatively useful. Okay, this one is a version of question 15, and a child pulls a sled through the snow on a level path with a force of 70 newtons exerted at an angle of 44 degrees. Oh, a nice easy one. Here's the ground. That's a sled. This angle is 44 degrees and the force is 70 newtons. And in this question, you're just simply being asked to calculate the horizontal and vertical. So horizontal is X component and vertical is Y. So if you want to know the horizontal, which is the X component, it's the magnitude times the cosine of the angle. And if you want to do the vertical, it's the Y component. And that is simply this guy times the sine of theta. So it's going to be a 70 times a cosine of 44 degrees and a 70 times sine of 44 degrees. And do I know? Well, I've got the answer here. I might as well just use it then. According to what's in front of me, it's 50.4. And this one is 48.6. If this angle was 45 degrees, right? If this angle was 45 degrees, wouldn't both these numbers be the same number, whatever that number ended up being, right? What's this one? Sixteen's pretty much component, so I'm not doing that. 17 is a quarterback throwing a ball, so this angle turns into 40 and that becomes an 80, so I'm not doing that. Oh, this one I'll do. Okay. It's question 18, or at least like it. And we have a thing going this way, and the force is 30 pounds. So that's going to be the magnitude essentially. And this angle in here is 45 degrees. Nothing too weird about that. Got another one down here, 14 pounds, whatever number your question ends up being. And this angle here is 30 degrees. And we want to know what is called the resultant force. So I'm going to call them things. I'm going to call this vector here U, because I have no imagination, and I'm going to call this one V. I've got to call them something. Then isn't the resultant force what you get when you add the two vectors together? And having a vague idea of what's likely to happen, would you agree that the resultant force is probably going to look something like that black one? I mean, you can tweak it, but would you agree it's somewhere between here and here? And I'm saying it's about there. So what we're going to have to do here is we're going to have to find the component versions of U and V, and then just add them together. Right, let's do U. It's going to be the magnitude, which is 30, times the cosine of 45, and the magnitude that's 30 times the sine of 45. And for V, oh, well, let's finish this one off before I talk about V. If you do 30 times the cosine of 45, the answer I get is about 21.2. And in fact, I want to be 21.2 both times. Now, this guy is definitely going to be somebody, which is 14, times the cosine of an angle, and it's going to be 14 times the sine of some angle. But that angle is not going to be 30 degrees. What number will that angle be?
Not 60?
Nope. Keep thinking. Think of trig. How do you measure angles? (330). Could you also call it negative 30 degrees? Is that the one you were thinking earlier, Molly?
Yeah.
Yeah, in which case, totally fine if that's what you're thinking. I'm just going to do the long way around, 330. 330. And if you do 14 times the cosine of 330, you get about 12.1. And if you do 14 times the sine of 330, you should get a negative number. Oh, good, you do. You get -7. So won't the resultant force be these two added together? So that's 33 point, oh, that's an interesting number. 33.3. And when you add these together, you get to, I believe, 14.2. Are you happy with the resultant force being add the x's, add the y's? Now, they don't want to know that, although you need to calculate it. What they're asking in this question is the magnitude of the resultant force and the angle that it makes. Okay, let's go for magnitude. I want to know the magnitude of that vector. Isn't it just square the two and add them inside the square root? So it's just a big messy number. It's 33.3 squared, 14.2 squared. So I go to the calculator and I do square root of 33.3 squared plus 14.2 squared, and I get about 36.2. And the angle, which I'll call theta, is the inverse tan of y over x. So if you just use formula, I don't need pictures. But if you want to do that little right angle thing that some of you were mentioning, that will work as well. So it's going to be the inverse tangent of the y component, 14.2, over the x component. So inverse tangent of 14.2 divided by 33.3, and the answer we get is 23.1 degrees. Are you comfortable about how these questions are created then? Right. So let me just show you the last couple and then we can move on. There's going to be a change to what's in your test and what's in your homework. The section that comes next is dot product, also called the scalar product. And that won't be in your test and it won't be in your homework, but we are going to do some questions from it. Okay. Here is question 19, very similar to the one I just did in 18. I think everybody's going to agree that this vector here has an angle of 60 degrees. What is this vector here, the one with 400n, going to be? What's its angle going to be?
180.
180, okay. And there's some working for you. And that one's a daft question, but you can see the answer. If you go A to B, B to C, and C to A, don't you just end up with the zero vector, which is that guy? And it's not the proof. So let's talk about our next section. At least we can get a start on it. And that means that after the test, we won't have so much work to do. I'm just loading the questions up. And let's nip it back to some notes. And what's this called? Dot product? It's called the dot product. So let's stick to that name. You will find it is called in some places scalar product. Now, the people who've seen vectors have probably came across dot product, right? Do you call it dot product or scalar product, or they switch the names around and nobody cares?
They switch it around.
Okay, so I occasionally I'm going to say scalar product by mistake. If you hear me say that, well, you just insert the word dot product in your brain and you know what I'm talking about. Now, let's do two vectors, vector u and vector v. And vector u is going to have u1, u2, u3, because we're going to do 3D vectors. And this one's going to be v1, v2, and v3. And imagine that this is u. And imagine this guy here, I'll make him a bit longer, make this guy our vector v. We would like to know the angle between the two vectors. Now, if you imagine these two pens represent our vectors u and v. Isn't the angle between them here? Right. So it's a real number, right? It's a scalar. It's just a number. And it's going to take a value. Well, let's see what kind of values it could get. If both vectors are parallel, won't the angle be 0? I could draw it so that the angle is 90 degrees. I guess that can happen. And isn't the worst possible scenario that the vectors are pointing totally away from each other? And when they point totally away from each other, what's the angle between the vectors going to be? How many degrees?
Is it 180?
It is 180. So if you're looking at the range of answers you can get, couldn't you get 0 degrees when they're both on top of each other? Kind of in the middle, couldn't you get 90 degrees? And then worst case scenario would be that. So if you ever think that the angle between two vectors is 200 degrees or minus 50 degrees, you're wrong, right? The answer has to be between 0 and 180, because what we're measuring is a physical thing, right? A real thing in real 3D world, right? And so keep your answers in the range 0 to 180. So the way we are going to actually find this is using a thing called the dot product. So let me tell you how to calculate the dot product. I'm pretty sure it gets its name because it has a big dot in it. You read this out loud as U dot V. So you say U dot V. And it's a number. The dot product is a scalar, a single number. And it's made up of these two guys plus these two guys plus these two guys. So far, so good. Is anybody going to tell me the other formula for calculating U dot V? But this formula has the angle theta involved in it.
It's the magnitude of U times magnitude of V times cosine of theta, with theta being the angle between the vectors.
Correct. Now, if you take this formula and you take this formula and essentially make this equal to that, can't you rearrange the formula and you get that the cosine of theta is equal to U1 V1 plus U2 V2 plus U3 V3 divided by the magnitude of U times the magnitude of V. And we tend to abbreviate this fella by just calling it U dot V again. So the formula for finding the angle between two vectors is the dot product, and by that I mean this expression here, divided by the magnitude of U and V. Now, as we don't like math to see things, wouldn't you agree that this formula could be expanded to fourth dimensional space, which is Einstein's for space-time? Wouldn't you just add an extra U4, V4? And if you want to do string theory, can't you go to 11 dimensions, which I believe is the last one I heard anyway. You need 11 dimensions for string theory to work. So we can even find the angles between two vectors that nobody in the universe actually knows what they look like, because our brain, we don't see things in 11 dimensions. We can't even fathom what that would be. So let's give you some questions where we get to do that. Let's suppose I have a vector U, 2, 3, minus 1. And I have a vector V, and it's 1, 0, 2. And I would like to know the angle between them. Well, I need to know some things. I need to know the magnitude of U. I need to know the magnitude of V. And I need to know U dot V. Well, the magnitude of U will be 4 plus 9 plus 1, which is the square root of 14. The magnitude of v is 1 plus 0 plus 4, which is the square root of 5. And u dot v is 2 times 1 plus 3 times 0 plus negative 1 times 2, which actually is 0. And so the cosine of theta is u dot v divided by these two guys, which happens to be 0 divided by the square root of 4 times the square root of 5, which I don't really care about because the answer is 0. So if you want to find out who theta is, you just find the inverse cosine of 0. And I guess I could have done that without using my calculator, but in general, you're going to be using a calculator, so I might as well do it. And you get a rather interesting answer. 90 degrees. These two vectors are at 90 degrees. Now, I'm not going to make any attempt to draw them realistically, but can you imagine that they look something like that? And
Okay, so
yes.
if these vectors exist in 3D, and if they're not on the same plane, which direction is 90 degrees in?
Well, the direction is the direction between the two vectors. So let's
Wouldn't two
suppose
vectors always be coplanar?
yes, unless they are identical, in which case there isn't a plane. Yeah, if you do two vectors, right, and you can always pass a plane through them. Can't you pass a piece of paper? So they lie on a plane. So the angle between the two vectors, if you're asking what is it in, it's this angle here. And it doesn't matter if I rotate this down the way or I rotate it any other way. As long as we keep them at 90 degrees, you see that angle there doesn't care orientation. So it's almost, orientation has no effect on the angle between two vectors as long as the two vectors, you know, rotate the same way. What would happen if I did a, right, so this guy is 90 degrees, before I forget. When two vectors are at 90 degrees, we would say that the two vectors are at right angles. Great, that would be one term. I don't like it, but we could use that. Couldn't we also say that they are perpendicular, which is a little bit nicer and great? But the one that I'd like us to use is the term that they're orthogonal. So if two vectors make an angle in 90 degrees, we say that these two vectors are orthogonal, right? Have you heard that name? Because I'm sure you've heard the first two. But if you heard orthogonal, well, you don't look like you've heard it.
I probably heard about it.
Right.
I'm just
So-
not making that connection right now.
Right, let's add this to your vocabulary. Orthogonal is a better term for two vectors being 90 degrees. And the reason why it's a better term is because when you move away from 3 dimensions up to 4, 5, and 6, which some people do, theoretical physics guys do some weird math, right? You don't really want to use right angled, because right angled is kind of the world we live in. What does 90 degrees look like when two vectors are in 7 dimensions? You see, it loses all meaning. And these two have meanings that really only exist in, 3D world. Orthogonal is a term that exists everywhere. So try and remember to use that guy. Now, what would happen if I got the cosine of theta was 0? Not 0, sorry. The cosine of theta was 1. What would the angle be? I mean, I could do it in my calculator. Inverse cosine of 1. I'm about to hit it. Anybody want to tell us?
isn't it 0?
Yes. What does that look like? Well, if that one looks like orthogonal, right? What does a 0 degree tell you about the two vectors? Right, they make an angle of 0, right? And doesn't that mean that the vectors are parallel? So now we have a relatively simple test. If I give you two really ugly vectors, right, 3 dimensions, right, 7, 8, 14, 9, some really ugly numbers, and I give you another vector with equally ugly numbers, wouldn't it be very difficult to tell just looking at their values that they were parallel? Right, parallel, right, same direction, different lengths, right? But couldn't I do this, which is basically just number crunching, and find out that the angle is 0? And if the angle is 0, that means that U and V are parallel. So we can tell if vectors are parallel now. One last special case. What happens if you get the answer -1? What's the size of the angle this time? And you're doing it right. It's 180 degrees. So aren't you looking at a situation where I think technically aren't the two vectors at least the lines parallel, but their directions are opposite? Which tells us if you're doing one of these questions, doesn't the cosine have to fall between -1 and 1? You're never going to get a question where the cosine of theta is 3.2. If you ever do a calculation and the cosine of theta is a number like 3.2, you've screwed up. Go and figure out what button you hit wrong in your calculator. So far, so good. A lot of you, I don't know how many, but a lot of you, because you've done vectors in other places, wouldn't this be revision for you? Maybe I describe it in a slightly different way. Maybe I use the word orthogonal and you didn't before. But majority of what I've done is what you've done before. Have you lot only done it with 2D, or do you do it with 3D?
I've only done it with 2D.
Only with 2D. Would you agree that moving it to 3D is no biggie?
It almost appears the same as 2D.
It is. It's just an extra number, right? Maybe visualizing it's a little bit harder, but you know, that's fine. Let's see. Oh God, let's not see anything. I just realized the time. Your test is on Monday. I wish I hadn't ranted on a little bit. Your test is on Monday. If you can hang about for a few minutes, I will tell you a little bit more about it. If you can't, watch the end of this video. I'm just loading up our screen so we can talk a little bit about it. It's mostly what you know. So remember what we did. Yeah, while we're doing this, put your last name in. You know, it's got the same rules. WebAssign's going to disappear on you and your Canvas will disappear, but you'll still be able to get access to Desmos and the 3D and all that good stuff. So let's nip down here. The dot product will no longer be in homework. It will be bumped down here, right? What you will be doing is the tail end. So there's 1, 2, 3, 4, 5, 6, 7. Okay, there are 7 questions. You won't get 7 questions. You'll get 5 questions. I don't know which ones I'm going to drop out, but never mind. I'll figure that out later. Let's tell you the ones I definitely know I am going to be giving you. You're going to get a question to do with Taylor's and Maclaurin series, guaranteed, right? So it might be, here's a function, find T3 of X, you know, that kind of question. Or it might be, here's a function, find the entire Taylor series. So that means you have to find a pattern. It might be, that's the two main ones. What else is there in that you might get? Oh, you might get it to estimate something, but I probably wouldn't do that. And so you're guaranteed Taylors and Maclaurens, which basically takes care of the first three. I don't think I'm going to give you anything in 10.1, because isn't 10.1 you just go to, the software and you draw a pretty picture. What I might give you is the calculus of parametric. So here's a parametric curve, tell me what dy by dx is, that kind of thing. Not really much I can do in the coordinate system, so I probably won't do anything there, but I will do stuff in vectors. So you will get, here's some vectors and do vector arithmetic on them, or you might get, you might get, force pulling this way, force pulling that way, what direction is the plane going in, what's its velocity. It's chronological order, so the first questions will be from Taylors and the last stuff will be from vectors. And there's going to be 5 questions.